US Physics Olympiad, year 2015, USAPHO, final exam. Problem B2. The nature of magnetic dipoles. Part A. A Gilbert dipole consists of a pair of magnetic monopoles, each with a magnitude Qm, but opposite magnetic charges, separated by a distance d, where d is small. In this case, assume that negative Qm is located at z equals 0 and positive Qm is located at z equals d. Assume that magnetic monopoles behave like electric monopoles according to a Coulomb-like force F equal mu0 over 4 pi multiplied by Qm1 Qm2 over r square, and the magnetic field obeys B equal F over Qm. First question. What are the dimensions of the quantity Qm? Second question. Write an exact expression for the magnetic field strength Bz along the z-axis as a function of z for z greater than d. Write your answer in terms of Qm, d, z, and any necessary fundamental constants. Third question. Evaluate this expression in the limit as d going to 0, assuming that the product QMD is Pm is kept constant, keeping only the lowest non-zero term. Write your answer in terms of Pm, z, and any necessary fundamental constants. Part B. An ampere dipole is a magnetic dipole produced by a current loop I around a circle of radius r, where r is small. Assume that the z-axis is the axis of rotational symmetry for the circular loop, and the loop lies in the xy plane at z equals 0. First question. Write an exact expression for the magnetic field strength Bz along the z-axis as a function of z for z greater than 0. Write your answer in terms of I, r, z, and any necessary fundamental constants. Second question. Let k, I, r power gamma have dimensions equal to that of the quantity Pm defined above in part A3, where k and gamma are dimensionless constants. Determine the value of gamma. Question 3. Evaluate the expression in part B1 in the limit as r going to 0, assuming that the product k I r power gamma equal to Pm prime is kept constant, keeping only the lowest non-zero term. Write your answer in terms of k, Pm prime, z, and any necessary fundamental constants. Question 4. Assuming that the two approaches are equivalent, Pm equal Pm prime, determine the constant k in part B2. Part C. Now we try to compare the two approaches if we model a physical magnet as being composed of densely packed microscopic dipoles. A cylinder of this uniform magnetic material has a radius r and a length L. It is composed of n magnetic dipoles that could be either all Ampere type or all Gilbert type. N is a very large number. the axis of rotation of the cylinder and all of the dipoles are all aligned with the z-axis and all point in the same direction as defined above, so that the magnetic field outside the cylinder is the same in either dipole case, as you previously determined. Below is a picture of the two dipole models. They are cubes of side d much less than r and d much less than l, with the volume Vm equal d cube. First question. Assume that r much greater than l and only Gilbert-type dipoles. Determine the magnitude and direction of B at the center of the cylinder in terms of any or all of Pm, R, L, Vm, and any necessary fundamental constants.